So, let's continue. I actually terminated the first section a bit before the break. So let's go on before we go into what images are. First of all, there are different ways how you look at images and how you work on them. So let's assume to the beginning you have your image, which essentially is just a bucket of pixels. You have no interpretation whatsoever on them. The only thing you know that the pixels have their position and they have their intensity. That's it. And depending on how you approach it, depends on your background. And if you go on the experimentalist, you look at the characteristics like problem-driven, you do it top-down, and often you have a reality-based model for how things appear in the images. So examples would be cell counting, porosity, and metrics like that you're going for. Then you go into computer vision approaches. Then you're more trained into working with signals, structures, and then you're more method-driven. The algorithms are more centered. You're also looking more into features in the image, and the model that you're working with is based more on the image itself than on what you see on it. And sometimes even engineer different features to do the problem solving. And examples are edge detection, a classic one in computer vision, and also face detection are typical examples of what you do with computer vision. And then we have the data scientific approach, which is more result-driven. And data science or in machine learning, AI, you usually have some training sets that you compare, and you want your data to be told into different categories depending on what the system has learned. So it's biology inspired. Many of these methods, they are based on the training concept, like the brain. And in principle, what it does, it's actually reinventing, rebuilding the image processing analysis from scratch with different approaches, even though it's actually using a lot of the computer vision things in the background. And what you're doing with it, you're capturing imaging and can also identify unusual events, so anomaly detection. And then we switch on to the image formation. So an image is usually formed through this workflow where you have some kind of source which gives some excitation. That signal is going through the sample or reflected from the sample. Then you get some response from that, and that response is collected by the detector. So the impulses, they can be X-rays, light, electrons, and so on. And what you're looking for are electron shell levels. You're looking at electron density, phonon energy, and so on. And the response can be absorption, reflection, phase shift, scattering, or emission. And finally, the detection could be different kinds. Could be your eye. That's actually the first detector if you have light. Light-sensitive film. You can have cameras of different types. You can have scintillators converting the radiation into visible light, and some kind of transducer feeling where you have the changes. And here's a list of different image sources. I'm not going to read it through, but it's in the lecture notes. And then the acquisition, there are two ways. One is the traditional direct imaging, where you actually get an image that looks like as you measure essentially something that looks more or less like what you're looking at. So it may be that the measurement is a bit blurry. It's maybe also flipped a bit, but then you can reconstruct it and you get something like this. So it still resembles what you had from the beginning. Then you have the indirect or computational imaging, where you acquire data in a different domain than the actual spatial domain that you want to look at. So you need to apply some kind of transform to the data in order to produce the image. So for example here, we have a method that produces a Fourier spectrum of the data, and then you need to do the inverse Fourier transform to get into the expected information. And this is how the traditional imaging essentially works. You have your source that goes through the sample, then there is a lens that does something to the image, magnifies it mostly, and then you get the image on the image plane, and that is what we actually measure. If you blow that up into more technical terms, you have your light source, which has some kind of beam profile, which is described by this BXY. Then we have the sample with some absorption or attenuation profile, which is SAB, and then you have free space propagation, which is a convolution there, and then you have even more optical transfer functions, and you have a little bit more information in the detector, and that brings up into this equation. And this is only for the monochromatic case. If you want to have the polychromatic or non-monochromatic, then you even have to add the wavelength of the signal or the light source into the equation, and then it gets even more complicated to work with. So this is actually an integral over the wavelength. And in the indirect computational imaging, you have the tomography is one case. In tomography, you have a sample that you rotate and take images while it's rotating, and then you get a lot of projections from different views. And these projections you can use to reconstruct a three-dimensional volume. You can also do this light field, so infinite depth of focus imaging. So this is one acquisition where you can see that you can go from far field to near field. You can also have this mechanical cantilever imaging where you have a little pin that goes through the sample, goes over the sample surface, feeling the elevation changes. And then finally we get to working what images are. And first of all, what is an image? The very abstract definition of what an image is a pairing between the spatial information, which is the position in the image, and some information, intensity, which is a value. So each pixel is a tuple of position and intensity. And mostly it's a 2 or 3 dimensional position, but it could also be 4-dimensional if you have, for example, have time series, or even could be spectral information, etc. So how we can bring these images into the computer, we need to do some sampling, and there are different things we need to consider. First of all, the world is continuous. So we have continuous intensity, we have continuous space, and there are no limits, so no boundaries. Starting with the boundaries, the camera can only see what the field of view allows, so that is already a limitation. And the positions and intensities have to be converted into discrete levels. So starting out with the continuous case, we have some intensity profile looking like this, and in the space, it's really a smooth image. When you start doing the sampling, you get discrete levels of the intensities, and you also get discrete positions within the image. Otherwise, you can't really fit it into the memory. You need to have an array of points. And an important thing, it's actually a thing that you have to distinguish between. There is the pixel size and there is the resolution. And unfortunately, the whole media community have kind of kidnapped the word resolution, because they say a camera has 5 megapixel resolution. That's not the resolution. Resolution is a physical quantity, and it's given by the optical system. And what they mean is actually how many pixels they have, and that gives the pixel size, but it's not really the resolution. So the sampling theorem here tells us that to see an item, you need at least 2 pixels to see the variation and tell it. Otherwise, you will get aliasing effects, which you see in the images as moire patterns, so ripple around the edges. Ripple you can also see in JPEG images when they have done too heavy compression, but that's a different thing. So looking at different pixel sizes, so we have this image, and if I do a downsize, so this is the original one, which is a bit more than 800 pixels wide. And if I do a downsizing of 2 by 2, on this screen you don't see much difference. But if I start doing the downsizing by 32 by 32, you start seeing the pixels. They are very big blobs all over the place. And you don't have very many pixels anymore. That shows already that the level of detail you can see in this image is much less than in this one. Sometimes you want to do this downsizing to save space in your processing. It may be sufficient to work with so small images for what you want to do, but you don't downsize it more than your smallest features allow. And looking at the resolution and different pixel sizes, if you have an ideal edge, it's going from black to white in one step. And that is usually not the case, what you have in a measurement system, but you rather see something like this smooth edge, and then the edge goes over several pixels. In this case, I would say over 4 pixels, you have to transition from black into white. And this actually gives you an uncertainty later in the analysis. If you have a very smooth image, you don't know where you have the edges very exact, and that can also give you problems when you analyze the images. Sampling intensity is the other one I mentioned that we can do. This original image was 16-bit, but now I downsample the intensity into 16 levels, but still you can see pretty well. I think at least now on the beamer you can't see much difference. So that one is okay, and that's actually also because of the eye cannot capture much more than 16 levels, in particular not with this beamer. When I go down to 4 levels, well, then it gets really bad, and then you can see that this is actually most likely not useful for what you want to see. But again, if you do 4 levels, it's also a question where you place the 4 levels in the whole distribution of gray levels in the image. Maybe it's enough. Who knows? So how many levels or bits are actually needed? When we work in a computer, we actually talk about how many bits each pixel needs. And typically images, they are integer, and they have mostly 8, 16, maybe 32 bits per channel. So for example, a normal camera on your phone or whatever usually have 8 bits per color channel. In the scientific cameras, we mostly go for the 16-bit cameras, so we have 65,000 gray levels. And mostly, depending on what you're doing, is if you have high contrast, you can work with few bits. If you have clean images, so little noise, you can also work with few bits. And in particular, if you have segmented data, you can even go down a lot with the bits. If you just have a black and white, you only need 1 bit, 1 or 0. If you go into having labeled data, then you need to maybe go up a several number of bits. Many bits is when you have low contrast images or very large dynamic in the data. If you have noisy data, and also if you have very smooth gradual changes that you want to capture. Floating point is actually real values. Then you have typically a fraction number, and that is in particular when you have very high intensity dynamics, because the floating point has one part, which gives you the value, and then the magnitude is also given in that one. And that is good for high intensity dynamics, quantification of physical properties. So if you want to link your gray level to, say, an attenuation coefficient, you don't want to use integer values. You want to know, for example, that it's 1.27, and that is when you need it. And also in algorithms, when you do a filtering, you usually want to use floating point values, unless you are really on tight bounds on how fast you want to process the data. But actually, I personally use floating point mostly when I do my image processing. And now we have only talked about the pixels themselves and that they have values, but in the whole image, you have a distribution of gray levels. And this distribution is shown with a histogram, which shows how the frequency of each gray level. And this sample here has this distribution. We can see there is very few values which are dark, and then very many which are bright, and that's actually the background here. And that's actually one of the first things I do when I get some new data. Plot the histogram. Then I know already a little bit about the distribution, about the gray levels in the image, how well distributed they are, if they actually fill up the whole 16-bit, or if I only have, say, 1,000 gray levels out of 65,000. That, from the histogram, you can actually learn quite a lot about the image already. And here are some details looking at the image. You can see that the peak is from the background. This lower part here comes from that region, and this mid part here is around the edges. So this is a transmission image, so it's where the material is thinner. Some examples. If you have a discrete image of that kind, you have, actually there are, I think, 5 gray levels or 6 gray levels in it. You have the background, which gives a high peak, and then you have these small dots. They have different intensity, and if you look very carefully, you can see that there is something here in between. And then all the structural pieces here, they come in this region here. And the reason why we have a spread is that this image is a bit noisy, so that gives you the spread in the histogram peaks. Here we have a neutron image of a camera, and it's actually pretty uniformly distributed except for the peak here, which is the background. And one special part is using a bivariate data. When you have 2 different image sources, then you can plot them in a bivariate histogram, and then you get this kind of 2D plots out of the histogram. This is for lecture 10, I think. And as I said before, the human eye cannot handle many levels easily. So here you can see what it looks like when you have 8 gray levels, 32 gray levels. You can still see some banded behavior here. And if you have 256 gray levels, the human eye sees it as a smooth surface. You can't really tell which one is the difference between two gray levels close to each other. So what we can do is actually play with the how we visualize the data, is that we can play with the brightness, for example. Then we only look into a small window of the data and put the whole intensity on the screen for this interval. And then you can see here, we get an enhancement or contrast enhancement in the regions which are in the interval. Outside, it's just white or black. And if you go up here in this region, it doesn't happen very much. So here you can see that's only on the boundary, you see some gray levels. In the middle, it's completely black, and outside, it's white. The other one is to work with the contrast. It's actually how much of the histogram do you want to show. And here, if you show the full histogram almost, then you can see all the gray levels inside. But if you narrow it down, as you saw before, then it's only a little fraction of the regions that you can see with some gray level. But those regions you can at least see with good contrast. So let's create an image. Here comes a little bit of code, and I'm using something called a pandas data frame here to create it. It's actually a little bit overkill, but it's a nice way to show the table. So let's create a mesh of two images, the coordinates here. So here we have the x and y coordinates, and for each we create also some random value for each coordinate. So this is one way of showing the table. Here we're actually showing the tuples of position and intensity, but it's very hard to interpret. So it's actually better to viewing it as a visual image. When you have few pixels, it's actually even possible to show the intensity value on each pixel. But as soon as you go beyond, I would guess, 20 pixels in each direction, this is very cluttered and you will not have any help of it. The reason why you would like to do it would be if you are developing an algorithm, for example, and want to see what the levels, how the levels actually are affected. So it's a guide for you to see the levels in that sense. Typically, what you should have always when you do some analysis and present it is to have a color bar on the side. I will come to that as a side note in one of the lectures later. And what you also can do, until now we showed only gray level images. You can, of course, put colors on the image. And here you have to make the distinction between true color images, like the ones you get from your camera, or colorized images where you just use a color map to enhance or visualize different things. So sometimes it's actually easier to detect features if you put a color map on the data. Here are some examples on the random images. It doesn't really make so much sense, but you can already see that there are differences in how these color maps behave. The blue one and this one, they are kind of monochromatic, but they put the color scale on it. And the jet map is a bit different. It's really a polycolor image, color map. And depending on what you want to highlight, you use one or the other type of color map. And then there are many different kind of color maps. And in principle, nowadays, the recommendation is never to use the rainbow color map. It's mostly misleading, and it's often hard to associate different values to it. And in the end, it doesn't come out good in print either. The rainbow color map is very confusing if you get it in black and white. The other two, on this example, they will print as a nice grayscale. That one will be very confusing because the blue and the red here, they are on different sides of the color bar. They will be printed both with the same intensity in the gray. So that is one reason not to use it. And in this plot, in this list here, let's see if I can get my mouse here. There is a lot of different color maps in Python and also in other software. And yeah, there is plenty to choose from. I'm usually just using the traditional one, that's the default one, which is Parallel, or let's see, what's it called in MATLAB? Is it Parallel in MATLAB? And yeah, anyway, it's a green, yellow, blue color map, and that's actually pretty nice, I think. And here you can see how the different color maps work in the for the color channels, because in the end the color map is in principle taking one value and associating it with the three color channels, red, green and blue, which the computer uses. So here you can see that the blue one is more or less always going downwards, and this color, let's see, this is the jet map, and then here we have, I think that is the hot map, yeah. But they are jumping a little bit up and down in the color scales. Yeah, so it's usually just a lookup table that translates the intensity value into some color. And here you can see what the color maps look on the wood sample. There you can see the blues, the jet, and the viridis. Viridis was the name, sorry. Viridis and Parallel, they are about the same color map, depending on where you work with it, if it's MATLAB or Python. And when you do it, you can see here, when you show an image in Python, you just do imshow, img, and then you say which color map you want to use. Then you can also play a little bit with how you use the color map. You can do a nonlinear mapping, and with that you can also put more focus on different regions of the image. So here I'm using the same, but this is the linear scale, and when I do the logarithm of the data, of the intensity, then I get something like this. And the effect is I can get better contrast for different things. So here you can see this piece here, this probably is on soft matter, appears much better in the grayscale logarithm lookup table. And if you try visualizing it with the hot map, you don't see it at all, apparently. When you work with images, you can do also some arithmetics. So it's a pixel-wise operation. So you can do all the arithmetics. You can also apply scalar value functions on each pixels. But you can also, with different commands in essentially any image analysis toolbox or tool, you can compute the average value, you can compute the standard deviation, you can compute min, max, median of the data, computing that as a global value of the whole image. And what you can do with the arithmetic functions, for example, is the normalization, an operation that is done essentially on most imaging applications, where you normalize the image, where you have the acquired image, which is this one, and you subtract the dark current. That is a bias that is given in the camera. So it's essentially, it's just a black image or constant level at a low intensity. And then you divide by the open beam, so that's the beam shape that you're working with. And here you can see the beam shape, which you actually also see in the background here. And when you do this normalization, you have a very nice flat image, which is actually what you want to work with. For the transmission imaging, then you actually also mostly compute the negative logarithm so minus logarithm of this normed value. And then you come into the optical density image. 3D images is more or less the same as the 2D, but the tuple of position has now 3 coordinates, and it can be either a volume, but it can also be a time series of 2D. So a movie can be seen as a 3-dimensional image when you do the analysis. So in this example here, I have a little bouncing ball, which bouncing up and down, and when you look at this image, you can actually look, instead of looking at the frames x, y, you can look at yt at a certain position, and then you can see very nicely how this bouncing ball is following a trajectory over time. And well, the 3D images as an array, it looks like this. So you just create some image. And this is just 0 to 26, so it's not very exciting, but what you see when Python is printing it, you get a bunch of 2D slices that is lined up after each other. And that can be looked at in this way, that you do a montage where you take the slices one after the other in a big image. So in this case, we only had 3 slices, so we have 1, 2, 3, and the last one is empty. So this is a different way of how you can show it. You can also show it as a movie, where you go through the slices in some direction, or you can do a 3D rendering, but that requires a little bit more work to get there. 4D is yet another dimension up. Could be that you have a time series of volumes, but it could also be a hyperspectral image. And you could have, for example, multiple values per pixel. In this case, we have an example where we have intensity and transparency, but it could also be a full spectrum over some wavelengths. And showing this, you can do it either as showing the intensity and transparency separately, but the other way would be to do some kind of color coding and size coding based on so you show the intensity, and the blobs, they are coded by the transparency. So that's a different way of how you could show it. And then we have the hyperspectral. In that case, for example, if you do images with Raman spectroscopy, every pixel has a full Raman spectrum behind it. And that's a different kind of information. And looking at it, we would have different wave numbers and value. So the coordinates are actually x, y, and the wave number, and then some value. And then it could be that each pixel looks something like this if we would plot it. It's quite messy, actually. And finally, before we end today, I will go into a little bit about workflows for image analysis, because when you work with images, it's a lot of data, and a lot of data needs some computational strategy. And this is actually for the last lecture in May. No, was it May, or is it? I think it was in May, yeah. The important thing is that when you work with image data, a single CPU takes a long time. If you can work with many CPUs, of course, if the code is prepared for it, you can speed up. Ideally, with a quite a factor, like the factor of CPUs you have. And that is also actually an effect of Moore's law, that there are more and more transistors on each CPU, and these transistors are not put into a single CPU, but on multiple cores in your computer. And with that, you need also to use the programming paradigms for parallel processing to be able to really use it. And this is principle saying what I said before. So parallel coding is something that is important, and there are Python libraries that can support it, but in the base case, in the default case, it's usually not parallel. So that you have to be aware of when you do your processing. But there are ways to bring it over into the parallel. And the other thing is also available resources. Traditionally, people have one workstation, they pay one big workstation and are really proud that they got the money to buy this heavy computer. But it's mostly not fully utilized, and sometimes it's even better to buy the computing resources from outside, and there are pretty many different resources for that. And actually, the cost of buying in on one of these, for example, Amazon machines, is pretty low. And you can specify how many cores of CPU, how many cores of GPU you want to use, and you only pay for it when you need it. And then you can actually get much lower costs for doing your processing. So this is also something to think about for if you want to do mass processing, or even go to the national computing centers to buy in on some beam time. Just to look at a little bit how it works with sequential code and parallel code, we have a little workflow here. I like to cook. So we have a simple soup. So what you do, you buy some vegetables at the market, then you go to the butcher and buy some meat, and then you come home and you chop off the different things, the carrots first and the potatoes, then you heat up the water. I would actually heat the water before I start chopping, but that's another thing. Then wait until boiling, and then you add the veggies and wait another 5 minutes, and then you add the meat and you let it stand there for a little while, and then you have your soup. So this is one sequence of ways to do it, but what you could do is instead rearrange it a bit. There is something missing here. Yeah, anyway, so this would be a different way of doing it. You could buy the things and then, that's annoying. Yeah. Let's see. I think it's easier to show it as these graphs instead. So the sequential case is that you have everything in one single sequence. That must be hidden, the other one, it was incomplete. But if you want to do the complicated, you could actually do it at separate processes, where you first buy the vegetables, and you chop the vegetables, and then you add them. And you can have a separate workflow where you heat the water and wait it for boiling. And these two must happen until that one can happen. And then you can also buy the meat and wait. And in this way, you can spawn off and let someone else do it. So, for example, you can tell your roommate, you go and you handle the vegetables, and I boil the water, and someone else goes and buys the meat, and we can be 3 persons doing this in separate small units. And then in the end, we get our soup. So this is one way of parallelizing things, that you can divide it into different tasks and only do it when it's needed. This one, we can actually also do that one in parallel. So let's say we want to do a lot of soup. Then we have 3 or 5 stoves, and 5 persons are standing doing the same soup. And then in the end, you got a lot of soup. So you can do both in parallel, and it depends on also the task, how you work with it, how you want to work with your data. In some cases, this one is the ideal case. In other cases, oops, wrong way. This one is the ideal. So it depends really on how you want to break down your workflow. And with that, we have something called directed acyclical graphs. And there are pretty many of these workflows out there. So we have the Dask, we have Spark, and TensorFlow, PyTorch, all of these different packages and resources, they actually have this kind of workflow where you, in principle, do lazy computation based on defining tasks, and then when they are needed, they are executed. And that also, of course, comes into the deep learning, that you also have in the deep learning, you have these neural networks, we have nodes and connections, and things are only computed when they are needed in the network, and in that way you can parallelize the things. And well, that was the end of today. And in principle, the conclusion is that doing science with images is a non-trivial task. You need to really work with it. And images, they can reveal a lot of information about the samples if you treat them right. And images can be abstracted as signals, and they can be also quantitatively analyzed. And for that, we need to have some proper workflows, and that promotes a repeatable analysis. Next week, I'm going to talk about data sets, data augmentation, and ground truth for the analysis algorithms, and I'm going to have a little technical session about data frames too at the end. And well, that was the end of today. Thank you.